It's a relentless cycle of calibration stabilization and error mitigation. They are constantly tweaking microwave pulses, refining the shielding around the processor and developing clever software tricks to try and cancel out the errors that inevitably creep in. The core metrics they track aren't problem solved, but things like qubit fidelity coherence times and gate error rates. How long can a qubit hold its state? How many errors happen for every operation you perform? So, a huge milestone for the entire field is the concept of a logical qubit. This is where you use many noisy physical qubits, maybe hundreds or even thousands, and bundle them together with a quantum error correction code to create a single, more reliable, fault-tolerant logical qubit. Demonstrating the first truly useful logical qubits is one of the biggest goals in the industry right now. Myth: it's all quantum. Reality: it's a hybrid system. Another common idea is that you run a problem entirely on a quantum computer from start to finish, but that's not how any of the current or near-term systems are designed to work. The reality is that these are hybrid classical quantum systems. The quantum processor, the QPU, is really more of a co-processor, kind of like a GPU in a regular computer. It's designed to do one very specific, very hard part of a larger problem, while the classical computer does everything else. So what quantum companies are actually building and shipping is the full software stack to make this hybrid model practical. This starts with the SDKs I mentioned earlier, which are almost always libraries. For a classical language, like Python, this allows a developer to write a single script where some parts run on a normal CPU, and then, for a particularly tough calculation, it makes a call out to the QPU. The SDK handles all the messy business of packaging that requests sending it to the quantum hardware and getting the result back. But it goes deeper than that. They're building sophisticated compilers and transpilers. A transpiler's job is to take the idealized quantum algorithm you wrote and translate it into the specific set of operations that their unique hardware can actually perform. It tries to minimize the number of operations to reduce the chance of errors. Then there are schedulers and control systems that orchestrate this complex dance between the classical and quantum hardware. The software is the essential, and often overlooked connective tissue that makes any of this usable at all. Myth: building AGI. Reality: targeting niche R&D. The hype can make it sound like quantum computers are on the verge of creating artificial general intelligence or solving consciousness. The myth is they are general-purpose thinking machines. The reality is companies are laser-focused on a handful of very specific, very narrow use cases, commercial and scientific areas where quantum has a theoretical advantage. Their customers aren't product teams. They're almost exclusively corporate and academic R&D departments. So, what are the target applications? Biggest by far,